It'd be a lot messier than I anticipated that it should if we start messing around with all the shifting stuff right away today. So I decided to go ahead and just do hyperbolas non-shifted because hyperbolas still have A values, B values, C values, where A is still that distance from your center to your vertex. B is your center to your co-vertex. C will be the center to your focus. The only thing that's going to be different is just how the actual equation itself looks. So what I did with first hour is that I drew what a hyperbola was, and as I was going through it, I explained and showed them what all the parts meant and how they look. Okay? So let's look at an example. So, excuse me, a hyperbola. A hyperbola is going to be basically two parabolas. Two parabolas. They're either going to go left and right, or they're going to go up and down. Okay? Because the formula will make them do that. What happens here is we have a center. And again, today, we're just going to locate it at the origin. I'm going to graph a left and right hyperbola to start with and kind of show you what the parts look like and how they'll be labeled. Then I'll show you how the formula is derived. In hyperbolas, just like everything else, we have a vertex. Let's make it real easy. We have a vertex, an A value, if you will. We have a B value that's called a it's not technically called a co-vertex, but I still call it that. I forgot what the name of it was. I think it's a minor axis or something like that. But now here's where things get a little interesting. In order for us to work with hyperbolas, what we have to do is we create this imaginary rectangle that encompasses the vertices and the co-vertices. We do that. And they always will be. From doing this then, what we do is we extend our diagonals. Here's what I mean. I'm going to extend my diagonals through the center, just like this. What those diagonals are now called diagonal asymptotes, slant asymptotes, if you will. Remember, an asymptote is a boundary line that you will never get to, but you can get infinitely closer to. Remember how we talked about this before? If you had an equation where it's like 1 over x minus 2, x couldn't equal 2, because you had an asymptote at that value? Kind of what it is, but it's not a slant. We actually spend quite a bit of time talking about slant asymptotes when we look at polynomials, especially when we do something like this. Yes, that's a thing. Anyway, if I go back to this one here, you guys will see really fast how easy something like this is to write about. When we talk about these slant asymptotes, the reason that we have slant asymptotes is because they hold in the boundaries of the curves. Okay, they're always holding the boundaries of the curves. The wider the asymptotes are, the bigger the curve. The narrower the asymptotes, the narrower the curve. It keeps it in check. Okay? Now, really easy to do is this has a positive slope up to right 4. What's the slope of the line that goes up to right 4? 1/2, isn't it? What's the y-intercept of that equation? 0. So this asymptote has an equation of y equals 1/2 x. This one has one that goes down to right 4, which means it is negative 1/2 x. So what's going to happen here is not only will we label, like we did yesterday with ellipses, we had vertex, co-vertex, foci. Now we'll have vertex, co-vertex, foci, asymptotes. But it's nothing more than counting your slope from the center, up and over. And that's why that's the main reason why we draw this box, because this allows us to see our slope rise over run. Okay. Not bad? Okay. Now, remember how we talked about that your curves always look at the focus? Now, if you think about it, that means if my vertex is here, is my focus on that side going to be to the right of it or to the left of it? It's going to be to the right of it. Now, yesterday when we found focus, remember they were moving inward? Today when we find foci, they're going to be outward. Now, here's what happens. The generic form of an equation of a hyperbola is this. When we deal with hyperbolas, the value of a, the a squared term, that doesn't matter. It's what comes first, x squared or y squared, which makes you know which way you're opening. If x squared comes first, it goes left and right. If y squared goes first, it goes up and down. The a squared, b squared makes no difference. So this is for your left and right, and this is for your up and down. It's what comes first, x squared or y squared. Ellipses, a squared tells you where it goes. If a squared is underneath the x squared, it's stretched left and right. If a squared is under the y squared, it's stretched up and down. That's the only difference. Yesterday, when we found that value of c for your focus, remember it was a squared minus b squared? Well, today, it's the opposite of that. It'll be a squared plus b squared. So our focus, you find it at a squared plus b squared is your c squared. Okay. Now, if we go to the example that I just drew out there, our a value was our distance from our center to the vertex. Our b value was our center to the co-vertex. So what's 4 squared plus 2 squared? Is it up there? 20. So the square root of 20 is 2 root 5. Isn't that this value here? So when it's that value, watch what happens. There's your focus. The hypotenuse of that right triangle from the center to the edge, that length is the length of a focus because it's outside of it. So you have your A value for your vertex. Your C value is your focus. Your B value is your co-vertex. We basically are adding in a value. Now, here's the crazy part about how to graph these. All you have to do is this. Hug your asymptote, go through the vertex, hug your asymptote. And that's what they look like. There's no variance to it. Yes, sir.
I think you've been a mentor.
Who? Nina. Nina mentor.
Go ahead. Yeah, you go home.
You have somebody here.
So all you're having to do when you graph these, it's a matter of plotting your values. When you make the curve, when you plot your curve, it is quite literally hug the asymptote, go through the vertex, hug the asymptote. That's how they look. What changes up here is that this value of C, or the box itself, you can imagine if the diagonals were narrower, then you'll have a tighter curve. If the diagonals were wider out like that, you'll have a wider curve. And it all depends, it really just depends upon the slope and how that works itself out. Okay? Yeah, whatever. Okay. I don't want you to do. That's funny. Okay. Let me show you one that actually has all the values to it. So write the equation of the hyperbola. 4x squared minus 9y squared is 36. And we'll go through the step. We'll label everything and do everything you're supposed to do to set this up. Excuse me. What's the first thing we're going to do? Divide by 36. Very good. We divide out by 36. and you're going to get x squared over 9 minus y squared over 4 is 1. Now, what variable came first, x squared or y squared? So which way is this going? Left and right. Now remember, you can always go back and verify it. Remember I told you on the apps button, there's the hyperbola? It tells you. If x squared is first, you'll have the little diagram that tells you to go left and right. If y squared is first, it's going up and down. So it's there. I'm not going to make you memorize it. Okay. You still have to know what A, B, and C and all that is. Yes, sir? Yes. If it was x squared plus y squared, you know, with a squared, b squared. If A and B are different, yes, it's an ellipse. A and B are the same. It's a circle. All right, so now you have your values. Well, what's a squared? Well, we know it does this. What's a squared here? 9. B squared, 4. C squared will be 9 plus 4, which is 13. So a plus or minus 3. That setup right there didn't change from yesterday at all, did it? A is always the distance from your center to your vertex. B is always the distance from your center to your co-vertex. C will always be the distance from your center to your focus. That always is the same. What changes up with hyperbolas is you just got to draw in those asymptotes. Okay? Center's at the origin. We haven't moved anything yet. We know it's got to go left and right because we made that little sketch off to the side so we don't forget. So our vertices, we just walk left and right 3. Our co-vertices, up and down 2. Make the rectangle. Make your asymptotes. The value of C is the square root of 13. The square root of 13 is more than what and less than what perfect squares? Yeah, it's more than 9, less than 16, so it's somewhere between 3 and 4. Here-ish and here-ish. So just like you did yesterday, now do you have all these values you can label? Yeah, so we label. Oops. We had vertex at, what was it, 4, 0, negative 4, 0. Co-vertex, 0, 2, 0, negative 2. Did I say 3? Thank you. Yeah, I said, sorry, thank you. It's at 3, 0, negative 3, 0. Thank you. Foci at plus minus 13, so it'll be 13, root 13, 0. Negative root 13, 0. Asymptotes. I go back to that little imaginary rectangle that we have. I had to go up how many and over how many? Up 2 over 3, so what's the slope? 2/3. So I have one equation that is going to be y equals 2/3 x, and one equation is going to be y equals negative 2/3 x. Now, tomorrow, what will change is, or when we get to shifting, what will change is that your y-intercept will be different, which means that you'll know what your slope is, but you'll have to use one of the ordered pairs just by using point slope. How many times do I have to open the door for you? You should. And now, oops, mess everything up. The very last thing that we do, the very last thing we have to do then is hug your asymptote, go through the vertex, and hug the other asymptote. Yeah. Yep, as my total. It is. I sure you. And that's, I mean, hyperbolas really aren't any extra work than an ellipse or anything. You just have to get the asymptote. And eventually we may or may not talk about, because it's just kind of fun. I'm trying to be an adult and it's not working right now. It's called a lattice rectum. Rectum? Damn near killed him. It's just funny. I'm an idiot. It's a segment that goes through the focus that touches the actual curve itself. The only reason I'm telling you that because on the math team there's a question on the test that does that, so I wanted to at least lay it out in case some of you might have to take that test. So I'm just saying it now. You're welcome. But it's funny. It's like we were at. You guys have all been to Inbodens, right? Yeah. I don't know if you noticed that they had a solar system up over in there, hanging in the ceiling, like a diorama thing. Our oldest son is 8, he's a 2nd grader. Daddy, look, Uranus. That's where he learned it from. Yes. And you know, Connor. Look, it's Uranus. Children. Let's do one going the other direction with a little bit of a weirder number. I wanted to walk you through one that went the other direction that also had a different values to it. Because sometimes we do wind up with some weird slopes. So if I have y squared over 100 equals x squared over 75, or minus x squared over 75 is 1, what direction is this going to go? Up and down, very good. This has to go up and down because the y squared comes first. So right off the bat, next to this, I'm just going to make a little sketch. Okay. And then I just start labeling everything. We know that our center is going to be located at 0, 0. So our a squared value is 100. B squared, 75. C squared, well, what's a squared plus b squared? So your a is plus or minus 10. B is plus or minus 5 root 3. And C is plus or minus 5 root 7, I believe. Yeah. There are 7 quarters and $1.75, yeah. What's that? Yeah, I did. It's money. It's $1.75. There's 7 quarters in it. 25 is square root of 25 is 5. 5 root 7. Jim, you got it right. He wasn't paying attention. So you start without. We know that our vertex has got to go up and down, so we have to walk up to our A value, up and down 10. You guys see why I don't like using graph paper? 5 root 3. Remember, that's the square root of 75. The square root of 75 is larger than the square root of 8, but it's smaller than the square root of 9, so it's somewhere between 8 and 9. That gives me my co-vertex, if you will. Yeah. Make your rectangle box. Asymptotes. Oops. Hi, Sam! What are you doing? We're doing asymptotes. On that mother function? Hey, save your weight for the lotus rectum. You damn near killed him. See how fast he ran out of that room? I love my job. It's great. All right, so you get your asymptotes. Real quick, slopes. Now, this is weird because you've got a rise of 10 and a run of 5 root 3. Is it okay to have a slope with a radical in it? Yeah, it's fine. Now, think about it. Your slope is 10 over 5 root 3. Okay? If I do that and I simplify that, you get 2 over root 3. You guys remember how to simplify that radical? Very good. Very good. Basically, remember what you're doing. You're multiplying by a factor of 1, which is the root 3's. So you get 2 root 3 over 3 for your slope. So your two equations we're going to have y equals 2 root 3 over 3 times x, and 2 root 3, negative 2 root 3 over 3 times x. Okay. When it gets time to having to write the equation, if it's not a clean intercept, like 0, I'll make sure that the values that we get. Hey, wait, I got 2 people in there? Wow, that's awesome. I can turn you up a little bit. All right, now, hi. Can I click on theirs? Oh, I see you. Hi. I think they're frozen. She's not moving. Is she alive? Where's Devin still there? Hi, Devin. He's still there. Okay. Crazy. That's awesome. So now, last thing is apply your C value 175. 175 is bigger than what? 169 and 196. Oh, all right. We're plotting. Now we're plotting other things. All right, we're plotting. Excellent. So we've got. They're everywhere. So you've got, so that focus then is somewhere between 13 and 14. There's square root of 175. And then lastly, hug your asymptote, go through the vertex, hug the other asymptote. They're ugly. They're kind of ugly. And that's, they just get to be kind of messy, but the process of setting these things all up, that never changes. Okay? It never changes. As we get into it more, then we will talk about the rectum. It is funny. We'll be able to figure out that length. It's pretty easy. Well, if you think about it, what's the y value here? The y value there was at what, 5 root 7? And then if that's 5 root 7, where does it intersect that curve? You just substitute it in the equation. There's a shortcut way of doing it, I'll show you. Now, just like we did yesterday, skip out. We also talked about how do you write equations if you know because they're learning stuff. Seriously, it's the first time I've dropped it all year. No, I'm not lying. That's the first time I've dropped it. I spin it all day long. You know that. Foci vertices. If we're talking about in terms of A, B's, and C values, remember, value of A is from center to vertex. B, center to co-vertex. C is your center to the focus. So what we're looking at starting today here, obviously we have everything centered at the origin. See you, Sam. Bye, Devin. You have this value of C as your center to your focus. So if you think about it, if my focus is at 13, nobody saw that. If my focus is at 13, negative 13, nobody asked you. And the vertices are at 5 and negative 5. What direction is this opening? Yeah, it's up and down. This has to be open up and down. So what comes first? X squared, y squared. Y squared. So your y squared stuff comes first. So you're going to have a y squared over a squared. X squared over b squared is 1. It got caught on my keys. Now, what's your value of A? It's 5. You're right, it's 5. Your A value is your distance from your center to your vertex. It's 5. Which means if A is 5, A squared is 25. Okay? Your center to your focus is your C value. That was 13. So what's 13 squared? It's 169. Which means you have to go back and think about, all right, it's A squared plus B squared to get you C squared. So 25 plus what is 169? How much? 144. And you don't have to graph it. You don't have to label anything. It's just write the equation. So you know where the values go. So you wind up with y squared over 25 minus x squared over 144 is 1. Doesn't it, when you write equations out like that, given the vertices and whatnot, it doesn't. You don't have to do really do any math. Except counts. Now, the questions that I put up, I think I already put them online too. I believe it started at 37. I had you guys doing 37 through 41 and then 57, 63. So 37, 41 odd. Now, I want to show you something here, 619. I want to show you a little trick that happens on some of these problems from time to time. And how do you alleviate a fraction? So, on number 37, and I had forgotten to show this in the first hour, so if you guys see anybody in first hour, tell them how to do this.